Okay, in the previous video, we learned about the nucleation process, part of the solidification of metals. Okay, so one of the things that was covered under nucleation process was critical radius. Okay, you should remember this term, critical radius. It is the radius that the embryo needs to achieve before it turns into a nucleus that can grow into crystals. Okay, so critical radius is important. Okay, so we're going to look at what factors affect this critical radius. Okay, so critical radius here is denoted by R prime or R star here, the symbol, and is 2 gamma. Gamma is a surface free energy, so I'll touch on that soon. Delta HF is latent heat of fusion, heat required to change between liquid to solid phase. Okay, you will learn more about this in another subject, thermodynamics. Delta T is the amount of undercooling. Remember the example that I gave from 0 degrees to minus 10 degrees. Okay, so how many degrees are the metals undercooled below its freezing temperature? And Tm is freezing temperature. Okay, so what it says here is the greater the degree of undercooling, the smaller the critical radius of the nuclei formed. So if delta T is big, obviously this whole equation will be smaller, will result in a smaller number for critical radius. So higher undercooling, smaller the radius of the nucleus needs to be before it starts turning into crystals. Okay, so where does this critical radius come from? So basically, this process is influenced by two types of energy. Okay, so it's a volume-free energy, surface energy. Okay, so take a look at this graph. There are three lines that you see. This is the energy for the nucleation process, total energy. Okay, total free energy is a combination of the volume free energy and the surface free energy. Okay, so two things can happen during the nucleation process. So that is related to the critical size. Okay, if it's smaller than the critical size, then it will dissolve. If it's bigger than the critical size, it will grow into crystals. Okay, the nucleus will grow into crystals. So the black line here is the total energy. This is the surface energy, and this red one is the volume energy. Okay, so what you see here is volume energy will reduce as more liquid turn to solid. Okay, as more liquid turns to solid, the energy will reduce. Okay, but at the same time, energy is increasing because more surface is formed. Okay, so basically what happens is at this point, at the critical radius, this is the turning point. Okay, what happens before this point? Okay, below critical radius, energy is lowered by redissolving. This is what happens here. Okay, it's forming, redissolve, forming and redissolve, forming and redissolve. But if it reaches this point, energy is lowered by growing into crystals. Okay, so past this point, the energy also will be lowered by growing into crystals. So this is the maximum energy. This is the point that the embryo needs to reach to turn into a nucleus. Okay, so let's come back to this equation. So we're going to try and use this equation at least once in this video. Okay, so these are the values that you could refer to. If you are trying to solve the question by yourself afterwards, you can always um, pause at this point. Okay, or you can access the lecture notes that will be provided. Okay, so in this table, you'll see the element. These are their freezing temperature, either in degrees or Kelvin. This is the heat of fusion parameter. Okay, this is the constant. This is surface energy. And this is maximum undercooling. So look at this formula again. Gamma is the surface energy. Heat of fusion is a delta H. Okay, so heat of fusion, this is your surface energy. Okay, so let's try one question. So calculate the size or the radius specifically of the critically sized nucleus for pure platinum when homogeneous nucleation takes place. So what is the critical radius of platinum during homogeneous nucleation? Very easy, we just use this formula. Okay, we use this formula. So the formula is here. We just need to find the right information. Okay, so from the table, you'll see that gamma is this value for platinum. The heat of fusion is this value, also from the table. And Tm is the freezing temperature. Okay, this Tm. And for undercooling, we're going to use this formula. It is 20% of Tm. Okay, you will see that in the table there's a maximum undercooling observed. So we're not going to use that. We're going to use 0.2 times the freezing temperature. Okay, so here you have to be consistent. If you're using Kelvin, use Kelvin for both. Okay, so substituting 2, this is your gamma, times freezing temperature, this is the latent heat of fusion, and the delta T. Okay, and then you should get this answer. So make sure the units are consistent so that you can cancel out as necessary. Okay, so cancel this, so you're left with Cm. So you can try the other two. Okay, you can try question 2 and 3. The solution is provided in your lecture notes. Right, so that's it for this topic. We have covered homogeneous nucleation, and the subtopic here is the critical radius. Okay, so we've learned that. We've covered heterogeneous nucleation and the formation of grain boundaries. So in the next topic, you will learn about the types of solid solutions that are formed.